Hello students, good afternoon to all of you.
Good afternoon.
Am I audible?
Yes, ma'am.
Yes, I'm audible.
Yes, ma'am.
What we have done in last class, have I discussed component?
Yes, ma'am.
Yes, ma'am.
Okay, cut vertex and cut edge, bridge.
No, ma'am.
No, ma'am.
Okay. So I think we had done up to this one, right?
Ma'am,
Your
screen not
Ah,
visible.
oh,
brain is not
yeah,
visible, ma'am.
yeah. Now
Ma'am, now it is visible.
it's visible, right?
Yes, ma'am.
Yes, ma'am.
Okay. So we have discussed component. Component is maximal connected subgraph. Okay. We'll take the connected subgraph and largest part. Okay. You cannot take, for example, in this one, you cannot take this C3. You cannot say this as component. Okay. The largest part, maximal part. This is not the subset of, or you can just say which is not the subgraph of any other subgraph of G. Okay. Yeah. How many components it has? G?
Four.
4. Right? And if G is connected, how many components it can have?
One.
And if the number of component is 1, then can you say G is connected and how? Number of component is 1 means to say maximal connected subgraph of G is just 1. Okay, and we know that G is the subgraph of G itself, right? And we are also saying that this type of graph, the maximal is just 1, right? Okay, so that maximal has to be G itself. Okay, and we know that connected is that is maximal connected, that is component is subgraph, right? And connectedness we are just saying from here. Okay, we started recording. As you can see over here, it has one component, right? It is connected. Okay, sometimes we'll use this result to prove connectedness in Z, that is Z is connected or not. Okay, that is what is the definition of connected graph? When you say any graph is connected, by definition I defined on the second day, I think. Yes.
If the graph is joined by some path, then it is
Every two vertices are joined by some path, right? Every two vertices are connected. Then we say the graph is connected. So one you can prove by definition, or either you can show any two arbitrary vertex you can take, and there exists a path x2y. Okay, there is some path x2y, or you can also show number of component is 1, right? This is if and only if means this implies this and this implies this, right? Like this you can remember for connectedness. Yeah, this component, this G has 4 number of component. If I add some edge, then number of component will increase or decrease, or will remain same. Yes,
Remains same.
Could you please repeat?
remains same. But if I add this edge,
Then decrease.
decrease, right? And if I add instead of this adding this one, if I add this edge, then remaining
Remains
same,
same.
right? So what you can conclude from here? Either adding an edge, addition of edge, either decreases the component by 1, right? Or it is remaining same, right? Clear? You can add this one, number of component got decreased by 1, right? If you add this edge, remaining same. Clear? One edge at a time, I'm just saying. So adding any edge, statement I wanted to make, adding any edge decreases the number of components by at most 1. Clear? Whether it will be 1 or it will be 0, right? Means there is no decrease or decreases by 1. Now, if I delete some edge, then what will happen?
Remains same or increase.
I1.
When remains same?
When in a same subgraph, one is removed
From which graph?
from the second graph.
Second graph. If I remove this one, then
No, ma'am. UT.
UT. Okay, UT. This edge means you are removing. You can remove any of this one, or this one. Any edge which is present on some cycle. Okay, that will not increase, right? Okay, and if you remove the edge which is not present on cycle, then what will happen? Either this one or this one or this one or this one. Then number of components gets increased by 1. Clear? So addition is decreasing the number of component by at most 1, and deletion is increasing the number of component by at most 1. Is that clear?
Yes, ma'am.
Okay. If clear, then I think you can prove this. Every graph, this is the proposition, with n vertices means order n, right? And k size, number of edges, has at least n minus k component. You can check it. You take any graph with n vertices, with some vertices and some edge. For example, you are just taking this one, this graph. This is a graph with one edge, 4 number of vertices. So according to this statement, what should have? It should have at least n minus k number of component, right? Means to say 4 minus at least there will exist 4 minus 1. That is at least 3 number of components there will exist. Clear? Now if it has two number of edges, either this one or you can have this one, then 4 minus 2, and you know that there exist 2 component, right? At least 2 component, right? And it has exactly 2, so that is fine. What about if I add this edge? Means if we have 3 number of edges, 4 number of vertices, so how many component it should have? At least
1.
n minus k, that is at least 1. It is having 2, so 2 is satisfying at least 1.
Yes, ma'am.
So I hope it is clear. Clear? Every graph with n vertices, n number of vertices and k number of edges will be having n minus k number of component at least. Okay? That means lower cap it is given. Okay? Now, how to produce any graph? You can, if I give you n number of vertices and I want a particular type of graph with k number of edges. So what you do? Start with n vertices and just keep adding edges. Okay, till you are getting k number of edges. Clear? So starting with n vertices, you can form any type of graph. Clear? By adding k number of edges, right? Are you getting my point? Hello? Hello?
Repeat again, ma'am.
Am I audible?
Yes, ma'am. Yes.
Okay. So what I will start with n vertices, just n vertices. And n vertices we denote by kn complement, right? How many number of component it has?
N.
N number of component, right? Now I will add one edge, means total k edges I will add, but one by one. Okay. So after adding one edge, number of component in kn plus one edge e1, you can just say first edge. How many?
N minus 1.
It will be exactly n minus 1, right? Then again add one more, kn plus e1 plus e2. Exactly how many you are getting? N minus 2. Okay. At the time of third edge, you can form, for example, these two edges you have added like this, right? With n minus 2 component. Here n minus 3 vertices are there, right? So n minus 3 this one, and one component is this, right? So n minus 2 component. While adding third edge, I can add in between this one or in between this one. I have two choice, right? So if I add over here, the number of component will be exactly n minus 3, right? For the third edge, E1, E2 and E3. Okay, clear? If I add this edge, this one, then it will be n minus 3. Clear? And if I add this edge instead of this one, how many number of component remaining? N minus 2.
Yes, ma'am.
Got it? So at the third edge, because whenever we have three edges, so there is a chance of forming cycle, right? So that's why in general I can just say it will be having at least n minus 2 component, right? Can I use at least n minus 2 component? N minus 3, not 2. N minus 3, right? This is lesser quantity. So the number of component, this one, I can just say it will be at least n minus 3. Means to say it can have n minus 2 as well, right? Then, and how I'm just saying, here also you can just use at least n minus 1, at least n minus 2. Why? Adding in s decreases the number of component by either 0 or 1, right? So why at most 1? Then number of component will be at least n minus 1, right? N minus 2. This is n minus 3. And so on. For 4, it will be n minus 4. And for kth number of edges, k number of edges, how many? How many? At least
N minus K.
n minus k. And you can for k and complement this one. Yes. Yeah. So next k and complement. That is n vertices. Can you form any type of graph whatever you want with n vertices and k edges, right? Clear? So
Yes, ma'am.
any g you can form here, and k of g, what you got? At least n minus k number of component, and that's what you wanted to show. I think understood. Yes. N complement has n vertices, n number of component. Addition of edges decreases. Here it is. Decreases by at most one. That's why I just written n minus one. In general, n minus two. For third, it will be n minus three, and for k, it will be n minus k. And with the help of these k edges and n vertices, you can form any type of graph, whatever it is. Okay, you can get any graph, and that's why we have shown it. Hmm? Okay. Now I'll discuss cut vertex and cut edge. Cut vertex. Its name suggests we will be cutting it out from the graph. Okay. Any vertex of the graph G, V, if we delete that vertex, results into increase in number of component. Okay. Is the cut vertex if this is happening. If we take out G, if we cut out this vertex V from G, the number of components will be strictly greater than K of G. That is number of component of G. Understood the definition? Yes?
Yes, ma'am.
Okay.
Yes,
Uh,
ma'am.
so is V in this graph is cut vertex? Is V cut vertex?
Yes, ma'am. No, ma'am. No, ma'am.
No. Now
Yes, ma'am.
how many number of components are in G has one, and in G minus V we have
Two.
2, right? So this is strictly greater than 1. That's why V is the cut vertex. Clear? Or in case of connected graph, V is in case of only in case of connected. I'm just saying V is the cut vertex if the removal of that vertex disconnects the graph. Clear? And in case of disconnected, if it is already disconnected, then increases the number of components. Clear? Okay.
Yes, ma'am.
Now here, uh, in this one, how many cut vertices? In graph H, how many cut vertices?
Zero.
0. You cannot remove if you remove this number of components 2, it was 2, and same is happening with this one, and same is happening with this one, right? Number of components doesn't change. That's why no vertex are cut vertex. Now, if uh, Can you say any vertex with degree? Degree I have defined now. Degree, that is the number of incident edges with B. In G, it has to be at least 2, 1 or 0. Can it be 0? Can it be 1? Yes. If for a V, for any vertex V to be vertex, degree of V has to be at least. Take these examples and tell me.
2,
2,
2 is correct. What about 3? It can be 3. In this one, V is working as cut vertex, degree 3, right? So, degree for V, if V is a cut vertex, then this implying degree of V has to be at least 2. Can it be 1? No, right? Degree 1 is if we remove it, we are having the resulting graph as again connected or number of components remaining same. Clear? For 1 degree, and for 0 degree the component increases. Increases or decreases? Decreases actually. For example, GN with this vertex, if you remove this vertex, how many component? 1. Earlier it was 2. So we want increase in number of components, right? So if V is the cut vertex, degree has to be at least 2. What about the reverse condition, converse condition? Is it true? Degree of any vertex V is at least 2, then V is a cut vertex. Yes?
no, ma'am.
No. Give me the counter example.
Then, for example, in H,
So in H, what we have? C3 part, you can take it. Degree is 2, but still it is not. Here, degree is 3, but still it is not the cut vertex. I hope you got it. This is only the necessary condition. Okay? Not the sufficient. Next is how many cut vertices are present in PN? PN, CN, KN. This one done. For a vertex to be cut vertex, degree is this one. This is only necessary condition, not the sufficient. P1, how many number of cut vertices? P1,
1,
1 cut vertices. That is, does it have any cut vertex? No. Right. P2. See, if we remove that vertex
0,
from P1, we are having components at 0. Not getting means deletion of that vertex is not resulting the increase in number of components. Yes. What about this P2? This is P2 as well as K2, right? P1, K1? No. P2, K2?
No, ma'am.
How many cut vertices?
0.
0. Agree one na? So cannot be cut vertex. And in K1 or P1, degree 0 cannot be cut vertex. Now P3. So
1.
P3, 1.
1,
So P4,
2.
2,
P5,
3.
P6,
4.
4. How can you relate with N?
N minus 2.
For Pn, N is at least 3. You have N minus 2 number of cut vertices. I hope everybody got it. Yes?
Yes, ma'am.
Pn and Kn.
Ma'am, for Kn always 0.
For Kn,
for CN,
for Cn 0.
no ma'am,
For
N,
Kn,
N,
for Cn N.
For Kn,
For Kn. What are you
ma'am,
saying?
for
no, ma'am, for Kn 0.
Kn
For
0.
Kn
For
0.
Cn,
N,
N or 0.
N ma'am,
Okay.
Ma'am,
Can you
0.
delete any
Ma'am,
vertex?
for Cn also 0. For
Uh,
Cn also
can you
0.
have any cut vertex over here? C3, C4? No, right?
No, ma'am.
If you delete it, you're having same number of components. That is still the graph is disconnect. That is connected, right? So instead of this N, it would be 0. Clear? What about this graph? Yes? Tell me.
2.
How many cut vertices are present in this graph?
2,
2, right? If you remove U, how many components are you getting? If you remove U,
4,
4.
4 components, right? This vertex and the other K3. Sorry, K2. 3 number of K2, right? And if you remove this one, you are getting 2 number of components.
2.
Okay? Clear?
yes ma'am,
In the same way, we can discuss cut edge. So wherever you had vertex, you just put edge and edge E whose relation increases the number of component. That is, if you delete that edge E from G, it will give you more number of components than in G. Okay. And this cut edge is also known as bridge because it will disconnect the graph more. Or means if it is connected, it will disconnect it, and if it is already disconnected, the number of component will increase. Clear? So in case of Pn, or you can start with P1, P2. How many bridges are there?
For P1, no bridge.
P1 no
P
bridge, P2.
one.
For P2, one bridge, right? This one. If we cut it, we are getting two number of components. For P2, how many cut vertices were there?
Zero.
Zero, right? No cut vertex, but one bridge, right? How many bridges are present in this G? This
9.
graph.
9.
Yes?
9 edges.
And three.
Three, right? This one, this one, this one. How many bridges are present in this graph?
One.
One. And what about this one?
Two.
Two. In case of Pn, in P3, two. In P4, P4,
Three, ma'am.
three. In Pn,
And minus one.
n minus 1. These are number of bridges. Okay. Similarly, you can find for Cn. In Cn, cut vertices were 0, and in Kn also cut vertices 0. But in K2, we have one bridge, right? What can you say about Cn? Hmm?
And
Which
ma'am,
bridge, which edge is becoming bridge? No, right? If you remove UV edge, you have this is present on cycle, and you have one another path U2V, right? So whatever the you can just say bridge is present on cycle, that will never be uh, the edge present on cycle never be bridge. Okay, and any edge which is not a bridge has to be present on cycle. Okay, that is the Condorcet case. How many bridges? So in Cn it was 0, right? In Kn, in Kn
zero.
0 except K2. For K2 it is
Two. Yes,
here n
ma'am.
is
Two.
not equal to 2. Here you have one bridge. Clear? In this graph,
One. One.
one this edge, right? What about in this graph and this graph?
0.
Cut vertices.
One.
In H1.
In H1 it is 0,
Hmm.
and it
0
H2
H0, 0 bridge, 0 cut vertex. And here,
one cut vertex is there.
1 cut vertex and 0 bridge. Yeah, this is the table. You can just have it. Have a look. EN, CN, KN, and these two graphs I included. Number of cut vertices, number of cut edges, or you can just see bridge. Are n minus 2, it is n minus 3 for PN. For KN, number of cut vertices 0, but for n is equal to 2, it is 0. Otherwise, 0. Right?
0.
For CN, both are 0. For this graph, this type of graph, you can have this one, and all edges are present on cycle, so that will not become the bridge. And here you have this edge bridge, and this vertex is cut vertex. 1 1. Clear?
Yes.
Now in CN it was 0 0 both. Clear? Both it was 0 0.
Yes.
So instead of removing one edge or one vertex, you can say, can we remove how many minimum number of vertices we can remove to disconnect the graph? If you remove one, it is not disconnecting the graph.
Minimum 2.
Minimum 2. So that is the vertex connectivity of that graph. Okay? Vertex connectivity. Clear? That is minimum number of vertices to remove from the graph is that the graph is more disconnected. The resulting graph becomes more disconnected. Or if it is already connected, the G graph is connected, that will become disconnected. And if it is already disconnected, then it will be more disconnected. That is, number of components will increase. Right? That is known as vertex connectivity. It is represented by kappa of G. That connectivity notation. Okay, kappa. What about C4, C5? This is C3.
Can you rewrite?
Uh, yes. Again.
Can you please rewrite?
Okay. The minimum number of vertex connectivity is what? The minimum number of vertices, or you can just say minimum cardinality of a set U, set of vertices U, such that G minus U, number of component of G minus U, strictly greater than this one. Okay? The minimum U. Okay? This one. Minimum U cardinality such that this one. Okay? This is your kappa of G. What about C5?
Yes, ma'am.
For C4, it's 2, right? Kappa of C4,
Yes, ma'am.
it is 2. What about C5? Or in fact, CN? It will be 2 again. You have
Yes, ma'am.
this one. You can remove one vertex, not disconnecting this vertex, right? Alternate vertex. So minimum 2 vertices you need to remove so that the resulting graph will be disconnected. So it is 2. But is it working for C3? For C3, how many vertices you remove is that the graph becomes disconnected. It does not hold for C3 now.
Yes, ma'am.
Here, if you remove this vertex, then connected. Second vertex, connected. Third vertex, nothing. Right?
Yes, ma'am.
So we can rewrite this statement. The minimum U sets is that either you are getting number of components of G minus U is strictly greater than K of G, component of G, or the G minus U become trivial graph, one vertex. Okay, either you are getting one vertex or you are getting number of components increase. Now you tell me about C3.
Ma'am, 2.
2, right? If you remove it, you are not getting the disconnected graph and also not getting trivial graph. Again, you can remove one more vertex. You are getting the trivial graph. Okay? So 2. So for all n greater than equal to 3, vertex connectivity of Cn cycle of order n, it is 2. Clear? What about kappa of Pn? How many vertices you need to remove minimum to disconnect Pn?
Ma'am, 1. One for n greater than equal to 2.
Yes, 1 for n greater than equal to 2. Right? For trivial, it's not
Yes,
right. It's 0.
ma'am, 0.
Yeah. For this one, you remove one vertex, and in whatever graph you have, if there exists cut vertex, for that kappa of G, that is vertex connectivity of that graph, will be always 1 if V has a cut vertex. Okay, that is G has some cut vertex. Clear? Whatever we have discussed, you can also apply on number of that is on edge. Okay, as it will be edge set, the minimum edge set, minimum number of edges to disconnect the graph. Clear? In that we don't need to add this triviality condition because we are not removing the vertex, just removing the edges. Vertexes will be n only. Okay, that is known as edge connectivity, and that is denoted by lambda of G. So this is your any set. I'm not saying minimum set. Any set of vertices U does that. This gives you either this one number of component after removing